All right, so now we're going to focus a little more in detail on specifically trig integrals. We've done some integrals that have had trig functions on them, but we're going to really focus on some strategies for how to deal with certain types of trig integrals. And the first theme for this is how do we integrate powers of sine and cosine if they show up in an integral. I'll remind you, this has come up before. If you have cosine squared x or sine squared x that you're trying to integrate, you're going to use one of the half angle identities. Okay, is the simplest way to do this. So cosine squared x is 1/2 times the quantity 1 plus cosine of 2x. If it was sine squared, we would have used 1/2 times 1 minus cosine of 2x. And so you simply are replacing it with that identity. The 1/2 can be pulled out. Integral of 1 is x, integral of cosine of 2x, 1/2 sine of 2x, plus constant, and you're done. What if it was cosine cubed, however? So if you get a cosine cubed, what we're going to do is a different strategy. We're going to split it up into cosine squared x times cosine x. And we're going to use an identity for cosine squared, but not the same one we just used. The idea is we're going to use, remember the cosine squared is also 1 minus sine squared x. That's probably the more familiar identity. And the reason we're going to use that is with this extra cosine hanging out here, we can now do a U-substitution. Okay, so we could let u equal sine of x, du would be cosine of x dx. It's a perfect match. That turns into 1 minus u squared du, which integrates to u minus u cubed over 3 plus a constant. Plug your u back in, and you've got it. So one of the themes when you're integrating powers of sine and cosine is if you have an odd power, if you have an odd power of a sine or a cosine, that's a good thing. And your strategy is to borrow one of the odd powers. So you're going to, in this case, you're going to break up sine as sine squared times sine of x. You're going to break that up and steal a sine from the sine cubed. And then the idea is this is going to be your du, as we saw in the last problem, which means my u is going to have to be a cosine. So I already have a cosine here, but what I'm going to do with the sine squared, because now I have an even power, is change that into 1 minus cosine squared. And I can now let u equal cosine of x. Du would actually be negative sine of x dx, so we would have to, I put the negative there, we'll compensate with a negative outside, but you're pretty much done from there, right? We can finish off the integral. There's my negative outside, and I distribute the u squared, and then I integrate u cubed over 3 minus u cubed over 4, and then plug back in my u, which was cosine of x, and we're done. Okay, so again, just to review, if you've got an odd power, that's going to be the strategy. You're going to borrow one of the odd powers, just one power, and that'll become your du. That'll leave you with an even power of sine, which you convert to cosine. If they had both been odd powers, then you could have borrowed from either one. You could borrow from a cosine and have a cosine sitting out here and change everybody in terms of sine, or you could do what we did here and borrow from the sine. So if they're both odd powers, then you have lots of options. Okay. Now, what if they are both even powers? That's where we run into more difficulty. If they're both even powers, then the borrowing from one of them is not going to help us out, because if I borrow a sine, I'm going to be left with sine to the first, and there's no way to convert that to just cosine. So if they're both even powers, we have to revert back to the half angle identities. For cosine squared, that's 1/2 1 plus cosine of 2x. For sine squared, 1/2 times 1 minus cosine of 2x. Multiply the 1/2s together, bring that outside of the integral, if you multiply 1 plus cosine of 2x times 1 minus cosine of 2x, we have 1 minus cosine squared of 2x, which we're then going to turn into, using the identity, that's going to become sine squared of 2x. Now we have an even power of sine. At least it's just sine now, right? Not both sine and cosine. And the way that half angle identity works, sine squared of u, let's say, is 1/2 times 1 minus cosine of 2u. So if I have sine squared of 2x, over here it's going to get multiplied by 2. It'll be 1/2 times 1 minus cosine of 2 times 2x, which is going to turn into a 4x. Bring the 1/2 out with the 1/4. I got 1/8 now, and now we can integrate 1. This is minus 1/4 sine of 4x plus my constant. Okay, so that's kind of how powers of sine and cosine go. Now there's a similar game, so to speak, that happens when you're integrating tangents and secants, because as you know, they both are connected to each other in the sense that the derivative of tangent is secant squared x, the derivative of secant x is secant x tan x, so they kind of show up in each other's derivatives. But it's a little bit different because of the derivative formula. So here I have tangent to the 4th x times secant squared of x, and this one is just a regular U-substitution. If I let u equal tangent x, works out perfectly because the derivative du would become secant squared x dx. So this is just the integral of u to the 4th du, which integrates to u to the 5th over 5 plus c, or tangent to the 5th x over 5 plus a constant. Now, before we go any further with tangents and secants, let's talk about the integrals of just tangent and secant. Oh, wrong way. Here we go. Okay, so the integral of just tangent by itself, we don't know any function from 21a whose derivative is just tangent, so we have to kind of work this out. If we think of tangent as sine over cosine, and do a u substitution, letting u be cosine, du is negative sine x, so I'm going to need a negative outside, it's going to turn into 1 over u du, which is negative ln absolute value of u, or negative ln absolute value of cosine of x. And that's fine. Some people like to remember the integral of tangent as negative ln of cosine of x. That's what you get naturally. I like to take it one step further because, again, tangent and secant have this thing, just like sine and cosine, where they seem to always show up in each other's derivatives, and hopefully in their antiderivatives as well. And it doesn't look like I get a secant here, but I can turn this into a secant. Remember, this negative is like a -1, and the property of log says you can float that up to an exponent to get positive ln of cosine of x to the -1, and cosine of x to the -1 is 1 over cosine, also known as secant. So I prefer to memorize, which you probably want to do, because obviously you can derive the antiderivative of tangent, but you're going to use this so frequently you'll probably just want to know it. The antiderivative of tangent of x is positive ln of the absolute value of secant x. And now, kind of as expected, the tangent and the secants go together. Cotangent could be done a similar way, where you break up cotangent as cosine over sine and do a u substitution, and you'll get positive ln of the absolute value of sine of x. Now, secant of x is antiderivative. This one's a pretty creative technique to try to find the antiderivative of it. What we do for secant of x is multiply top and bottom by a fancy form of 1. This is, okay, it would seem difficult to come up with this on your own. Don't worry, you don't have to. It's already done for us. But the way somebody figured out the antiderivative of secant was to multiply top and bottom by secant of x plus tangent of x. Seems kind of random. But look what happens if you do that. If you distribute the secant of x on top to give you secant squared plus secant x tan x, all divided by secant x plus tan x, and take a careful look at it, it's a perfect U-substitution. If I let u equal the bottom, the derivative of secant of x is secant x tan x. The derivative of tan x is secant squared. So it's a perfect 1 over u du integral, which integrates to the natural log of the absolute value of u. So your antiderivative of secant of x, and this one especially is probably good to just memorize so you don't have to remember the trick on doing that. The antiderivative of secant of x dx is is the natural log of the absolute value of secant of x plus tan x plus a constant. And once again, secant x has secant and tangent in it. Those functions seem to always be connected. Cosecant of x could be done in a similar way. I won't show it here, but the antiderivative of that comes out to be natural log of absolute value of cosecant x minus cotangent x plus a constant. Okay, let's go on with powers of tangents and secants then. So if you have tangents and secants in the integral, you want to be thinking u sub. And you know, one thought is, what if I let u equal tangent of x? Du would be secant squared of x dx, which I do have on this one. I have 5 powers of secant, so I could borrow 2 powers of secant to satisfy my du, but that would leave me with secant cubed x dx, and I would have a harder time trying to convert secant cubed x in terms of tangent. So it's worth considering, but let's try something else. What if I let u equal secant of x? Du is secant x tan x, which I can make that work as long as I know I'm going to borrow one of my 5 powers of secant. I'm going to break that up as secant to the 4th x times secant x tan x, so that now if u is equal to secant, this is going to be u to the 4th, not u to the 5th, u to the 4th, because I'm stealing one of the powers of secant to become my du. And then the antiderivative would be u to the 5th over 5, or secant to the 5th x over 5 plus a constant. All right, here I have the integral of tangent cubed x times secant cubed x. If I tried letting u equal tangent of x, that would leave me with secant squared of x, which I do have again, but then I'd be left with a secant x to the 1st power, and that would be not easy to convert in terms of tangent, right? So you're always trying to be left over with even powers of secant or tangent. So let's consider the other option, letting u equal secant of x. Du will be secant x tan x. So what I would do is steal a power from both the secant and the tangent, so that could become my du. My u is secant, so that's going to be u squared, and I'm going to be left with a tan squared x that needs to be converted to secant squared. And this is what I mean by it's good to have an even power, because we have identities, and most of the identities involve even powers. Here the identity is tan squared x plus 1 equals secant squared, which means tan squared x is equal to secant squared x minus 1. So that leftover tan squared x gets replaced with secant squared x minus 1. And then there's my secant squared x, and there is my secant x tan x dx. That's du, this is u squared, this is now u squared minus 1. Distribute the u squared, and you're on your way. What? So that becomes u to the fourth minus u squared, u to the fifth over 5 minus u cubed over 3 plus a constant, which then replacing gives me secant to the fifth x over 5 minus secant cubed x over 3 plus a constant. Okay. Now this next one is kind of a sneaky one, and it just seems to show up, rear its ugly head more than once in 21b and even in beyond, and I've seen this integral come up in 21d frequently. Secant cubed x is kind of tricky. The way we're going to do this is to first break it up as secant squared x times secant x. And you could play around with trying to convert that to tangent and seeing if a u sub works, but you'll probably realize you run into a dead end. So we're going to do integration by parts. We're going to let u equal secant x and dv be secant squared x dx. So du is secant x tan x dx, and v, which is the antiderivative of secant squared x, is tan x. Plugging into my integration by parts formula, uv minus the integral of v du gives me secant x tan x minus the integral of tan x times secant x tan x, which is simplifying secant x times tan squared x. If I then use the identity for tan squared x, which is secant squared x minus 1, and distribute the secant x, and then break this up into two separate integrals, I'm going to have, okay, can't forget about secant x tan x minus the integral of secant cubed x dx. This negative with this negative is going to turn that into positive the integral of secant x, which we just talked about, right? That is ln of secant, absolute value of secant x plus tan x. We know that one. But we've seen this before. Remember when we did integration by parts, my original integral was secant cubed x dx, and in the process of doing integration by parts, I end up with the same integral. And so what I can do is manipulate this to get my answer kind of in an indirect way by adding secant, the integral of secant cubed x dx to both sides of this equation. I end up with 2 times the integral of secant cubed x equals secant x tan x plus ln of secant x tan x. So to get the integral by itself, I just divide it by 2. So it's that integration by parts trick where you get the same integral that you started with. Now, one thing I have noticed with this is there is kind of a cool way to remember this antiderivative of secant cubed x dx. Because what is this? This is the derivative of secant of x. What is this? This is the antiderivative of secant x. So it just by chance happens to be that the integral of secant cubed x dx is the derivative of secant of x plus the antiderivative of secant of x, all divided by 2, plus a constant. Just coincidence. Okay, I got one more here. This one's kind of tricky for another reason. So I have this is a definite integral now, the integral of from 0 to pi over 3 square root of 1 plus cosine of 6x. And so one way to find out this integral is looking at that part kind of reminds you of the half angle identity, because we have that 1 plus cosine of 2x. Here I have 1 plus cosine of 6x. So if that was a 6x, and I kind of work backwards, that must have come from cosine squared of 3x. And then I just multiplied the 2 over here. So then I could replace 1 plus cosine of 6x with 2 times cosine squared of 3x underneath the square root. Okay. Now, okay, put a big stop sign here, warning flags here, right? Because one of the things this has come up, probably it's come up in 21A, maybe even earlier in 21B, you have to be very careful when you take the square root of something squared. Okay, remember that the square root of x squared, most people think it's just x, but that's not true. The square root of x squared does equal x only if x is a positive number. For example, the square root of 3 squared does equal 3. But if what's being squared is a negative number, the square root of negative 3 squared, if we believe the square root of x squared is x, then we have to say the square root of negative 3 squared is negative 3, but that's not true. What does it equal? It equals the negative of negative 3, right? So the square root of x squared, if x is a negative number, actually equals negative x, right? Because a negative times a negative would make it a positive number. So what that means is before we take the square root, we can't just like simplify the square root of cosine squared of 3x and just say that's cosine of 3x until we know whether what's inside is positive or negative. So down here. If you think about it, from 0 to pi over 6, when x is pi over 6, 3 times pi over 6 is pi over 2, which takes you on your unit circle to right here. But if you go past pi over 6, by the time you get from pi over 6 to pi over 3, you're going to go, if you plug in pi over 6 here, that's pi over 2 to pi. That's in this quadrant right here, where we know cosine is negative. So what that means is we have to break this up into two integrals. The square root of 2 cosine squared 3x from 0 to pi over 6 is just root 2 cosine of 3x. But from pi over 6 to pi over 3, the square root of 2 cosine squared 3x is negative. That's why I have this negative root 2 cosine of 3x. That's a huge big deal. You got to watch out for these. Then the rest of it is I can finish this off. Antiderivative of cosine of 3x is 1/3 sine of 3x. From pi over 6 to 0. Same thing here, from pi over 3 to pi over 6. Work through the math. I get my final answer of 2 root 2 over 3. Notice if you did not split this up, if you just wrote square root of cosine 2 cosine squared 3x as root 2 cosine of 3x, and you integrated from 0 to pi over 3, and you plugged in, here's your antiderivative. If you plug in pi over 3, that becomes the sine of pi, which is 0. If you plug in 0, it's 0. And you would have gotten 0, which, number one, is wrong. And one way to convince yourself it's wrong is if you thought about this function from 0 to pi over 3, thinking of this in terms of area, if you drew a reasonable graph of that, you would say, well, there's no way that could have been 0, right? So anyhow, I wanted to point that out. If you end up with the square root of something squared in 21b, be very, very careful. Okay.